So don't worry about spin too much. It's a physical property. If you want to understand it better from the modern physics view, take physics. I mean, learn it. It certainly it can make predictions that are more accurate than any other predictions on Earth. So there's something right about it, and you can't just say, "Oh, that's too hard," because spin is important. I work, as I said, in NMR, nuclear magnetic resonance, and we took advantage of the nuclear spin quantum numbers to do experiments that are very useful for chemistry, biochemistry. It's amazing and awesome. I love nuclear magnetic resonance, but that's digressing. Now, in the atomic and molecular realm, where quantum electrodynamics is the model that works extremely accurately, the forces, as I said, are mediated by exchange of photons, which are bosons, and they have integer spin, meaning in the case of a photon, it's spin 1. Electrons have spin 1/2. Nuclei have quantum numbers, spin quantum numbers that can be 0, 1/2, 1, 3/2, etc., etc. They're built of elementary fermions that are spin 1/2. But photons are bosons and have spin 1. And the photons are light particles. They have wave-like properties, but they're light particles that travel at, lo and behold, the speed of light. They're light particles. In the nucleus, the fermions are quarks, which have half integer spin. They're spin 1/2 fermions. All quarks are spin 1/2. And they have unusual charges. I mean, if the charge of a proton is +1 and the charge of an electron is -1, the charge of a quark in a nucleus is either +2/3 or -1/3. But in the nucleus, the strong nuclear forces hold these quarks together, and the force carrier particles, the bosons that are pertinent inside the nucleus, are called gluons, because they glue the quarks together. Now here's something that is quite amazing that I think should be emphasized in general chemistry, and that is the fact that the masses of the quarks that make up nuclei, that make up protons and neutrons that make up nuclei, the masses of the quarks are known. The mass of the gluons is 0. The mass of a proton is also 0 because they're bosons. But inside the nucleus, the sum of the masses of the quarks that make up a nucleus doesn't account for more than about 1% of the mass of the nucleus itself. In other words, the mass of any nucleus is much larger than the sum of the masses of the quarks and gluons that make it up. How could that be? Well, this is getting back to consciousness theory already. One theory that explains why that is true is that the particles are moving inside the nucleus at essentially the speed of light or close to the speed of light. So they have, as the theory of relativity predicts, a greater mass because they're traveling at essentially the speed of light. So the mass of nuclei that are so important for electromagnetism and chemistry and biochemistry, the mass of those nuclei is almost entirely due, or mostly due, to the relativistic effects of the ultra-high-speed processes occurring inside the nucleus. Now, that's bizarre. It just shows that if things are moving fast enough, close to the speed of light and stuff, you can create mass. And it's just consistent with the idea that ultimately all there is motion, changes in momentum. Everything is just happening quickly. What we think of as something that's very predictable, the mass of a hydrogen nucleus, a proton, which can be measured extremely accurately. 99% of that comes from the motions and the behaviors of the particles that make it up, the quarks and the gluons. So very bizarre. So again, I'll just repeat this because I think it's important. This observation fits well with the idea that in the ultimate analysis, consciousness mediates all changes in momentum, and that mass and objects are manifestations dependent on the space-time realm of the observing entity. I'm an observing entity. I can't see what's going on in the nucleus. I can measure the mass of the nucleus by doing experiments. It's way too big to, it's much too large based on the particles that make it up. What the heck is going on? Well, something is going on, and I believe it's consciousness. So we postulate yet another idea that ultimately all that exists are conscious-mediated changes in momentum, conscious-mediated forces. Mass and objects are merely manifestations that depend on the realm of the observing entity. Now, there's yet another little twist to all this advanced nuclear physics and atomic physics, quantum electrodynamics, quantum chromodynamics, etc. And that is this relatively new idea of the Higgs boson and the Higgs field. Now, I have to confess that I don't understand how it works, but the Higgs boson is supposedly the boson, like the photons in electromagnetism, like the gluons in the strong nuclear force. Supposedly the Higgs boson is the particle that confers mass to things. And I am not sure how that relates to the other idea that has been put forth, that it is all relativistic effects that give rise to the unusually high mass of nuclei in comparison to the particles that make them up. So I know this is pretty hairy. Please bear with it. We're going to hit another extremely important set of ideas in the next lecture, lecture 3. So that's it for lecture 2.